In this screencast, we're going to consider a steady state, one-dimensional in the x direction. So that means that our only velocity is u, incompressible fluid that's between two horizontal infinite or modeled as infinite parallel plates. And what we're going to do with this is take our x component of the Navier-Stokes equations and simplify it to terms that we can then integrate and set boundary conditions for. Okay, so let's go through these terms one by one. Since it's steady state, there's no change in velocity with respect to time. Since it's one-dimensional, w is 0, v is 0, and by the continuity equation, u isn't 0, but du dx is 0. On the left-hand side, we assume that there's a pressure gradient because nothing in the problem tells us that there isn't. We know that gravity is in the y direction, so that term is 0. If du dx is 0, then d squared u dx squared is 0. And finally, because we have two horizontal infinite plates, we can say that u does not change with respect to z. And so what we're left with is that 0 is equal to minus dp dx plus mu d squared u dy squared. So assuming that pressure is not a function of x, and then we can write it as a constant, and moving all the non-partial derivative terms to one side, what we end up with is that 1 over mu dp dx is equal to d squared u dy squared. So since this is a second order differential equation, we're going to have to integrate it twice to get our u of y. So let's do the first integration. So du dy, and I've switched these two, is equal to 1 over mu dp dx times y plus a constant. And now let's integrate this again, and we find that u of y is equal to 1 over 2 mu dp dx times y squared plus c1 times y plus c2. And so this is going to be the equation that we'll always start with when we have these particular conditions. So let's take a look at one case. So let's say that we have stationary plate and fluid, which is driven by the pressure gradient. So these are parallel, flows through them. And we're going to assume that they're infinite. So basically, we have a plate here, and we have a plate here, and we're going to have fluid that's going to flow through here and have some kind of velocity profile. So we're going to call this 0. This is going to be h, and this is going to be minus h. So because we have two constants, C1 and C2, we're going to need two boundary conditions. So we can say at y, and that's what we mean about boundary conditions. That means let's find a certain y and apply some form of the velocity to it. So at y equals h, we know that u has to be equal to 0 because the plate is stationary. In addition, at y equals minus h, again, it's stationary, so our u has to be equal to 0. If you note, I made the origin or the 0 in the middle of the plates. You don't necessarily have to do that, but because the flow is going to be symmetrical, because both plates are stationary, we often put the origin between the two plates. Okay, now we're going to look at a different situation. So we have a top plate that's moving at a velocity u and a bottom plate that's stationary. And again, we're going to want to use boundary conditions to find our u of y. And again, we start with this equation, and our boundary conditions for this particular situation are going to be, and here it's not symmetric, so we'll say that this is the 0, and we'll say that the spacing in between is h. And sometimes you'll see this spacing as h and sometimes as b. So we know, again, at y equals 0, that u equals 0 because the plate is stationary. However, here at y equals h, u is equal to the velocity of the moving plate. So if you notice, we still have the same Navier-Stokes equation that we use. However, what changes are the boundary conditions. And finally, what we can look at is if both plates are moving. And so here, with both plates moving, and we'll assume that they're moving at different speeds from each other. Now what we're going to say is at y equals 0, our u is equal to some constant u1, and then at y equals h, our u is equal to some constant u2. And so what we can do is apply these boundary conditions for any one of these situations to eventually solve for our constants. So we solve for C1 and C2. And when we do that, if we go back to our original equation here, what we find is that we now have a velocity profile that we can apply at any y.